Instead of using the IR sensors on the Domino Robot to follow a line, or even the IR remote, I decided to add some eyes to the Domino Robot so that it will actually see light and follow light. So that way I can use a flashlight, shine it on the ground, and it will actually chase after the light that I am putting on it. This little guy was the inspiration for the light following Domino Robot hack. Except this guy actually runs away from light. So when you shine the light on the sensors, it will actually start the motor and run away from the light. So one core takeaway from this one are the light dependent resistors, also known as photocells or photoresistors, that react to the light. They transmit information once receiving light, converting that into a signal that we can put into Arduino to inform the rest of the code how to react from the input of the light that this little guy, or now our Domino Robot, will be receiving. With the way the circuit is set up, the more light that you direct on the photocell, the less resistance that you have, meaning there's more power being pushed to the motor. And that's how the wheels move faster and turn the robot where you want it to. The cool thing is you could still use the domino dropping aspect of the Domino Robot while it follows the light. We can make some modifications to it so the timing of it works a little bit better, and then still use that aspect of it. Now, if you want to go a little bit faster and have it chase quicker, you can disable the domino dropping aspect like in the original one and just do the light chasing one. Ramp it up as fast as possible. It still doesn't move all that much, but once you get the best bright light on it, it will move pretty good. Let's go over the wiring for this setup. So you have the two LDRs, that is, you can kind of see here at the front aspect of it. The wires run underneath and then pop up through this little hole here. There are 3 wires per setup. You have your red and black for the power, and then you have the blue and green that are the signal. As normal, the black and red go on the normal spot. For the signal wires, which are the blue and the green wires, I have the left side, which is green, going into the A2 port, and the right side, the blue, goes into the A3 port. I currently have it connected by the USB, so that way I can see it in the serial monitor. And right now I have the left motor speed being reported out in the serial monitor. So right now it's ranging between the 239 and 240 with the lights that I have currently focused on it right now. So to understand this, the left motor, which is looking from the back side, this would be your left motor, and then your right motor. The LDR that drives it is on the opposite side. So when you have light coming here, you want to power on the right motor so that it turns, and vice versa. So for the left motor, I need this right LDR to be responding, and you could check this in the serial monitor by covering it, and as we can see, it's dropping down to 75 with it being blocked, and then back up to the 240. And if I add just a little bit more light, I can get it to max out at 255. So the 255 in the code is the top speed you can achieve. So we currently have it maxed out with its full potential using the code aspect of it. It does take some code to be able to integrate the sensors with the Domino Robot, but it's not too bad altogether. The first thing we need to do is define the pins to find the values of the LDR input. The signal wires are going into both the A2 and A3, so we need to make sure that those are defined. So in this section here, you can see that I have the macro name, very similar to a variable, LDR right for the A3 input pin. You just need to make sure that those are correct. So you have the A3, and then you have the A2 for the LDR and LDR right. To be able to use that information on an ongoing basis, we created these 2 variables to then take that data, apply it to a variable, and then be able to use that variable information ongoing. Now we started with 0 to make sure that there's no movement once it's initiated. Once we get into the loop where it's looking for more information, that's where we will grab the data from the pins using this analog read for both the left and the right. Then we apply it to the two variables that we created. Once we get that data for the variable, then we take that data, use it with the power wheels function, which we'll go over a little bit later, which tells what the motor speed should be for both the left and the right. Now, as you can see, the right LDR is controlling the left motor. So you have the right LDR, but for the left motor, and vice versa. Now, the rest of this is following very similar to what the code was originally, where it just takes the motor speed, puts it into this constrain function to then tell the motor what it needs to be driving. That motor speed variable then goes to tell the motor drive this speed. So this is the power wheels function that I created. It's an integer number that will be returned after it is evaluated. At the top, you can see the power wheels function now, where I take the data that is input from this section here. So it reads the data from the input, converts it into this function, which then calls this function to run the data output. Essentially, I'm giving it information. So initially, I want to see what the volts are that the input signal gave me, and I want to evaluate it. That's all this power wheels function is doing, is evaluating the data and converting it into something useful. Keep in mind that the PWM for the motors can only go from 0 to 255. So if I don't have a range that's within that, it's not going to work the way it's supposed to. So I'm converting the data into something that is useful as an output signal for the motors. So as I was looking at the data, I could see that you could actually max out your volt value from the LDR over 1000. Keeping in mind that 255 is my max, if I divide 1000 by 4, it keeps it at 250 as kind of a max number. So easily, I can take that number and divide it by 4 to get me within the ballpark of 0 to 255 to get that varying degree of power. Anything above 1000, I want to just hit the top speed, which earlier I made my top speed the 255 to max out. So if it hits more than 1000, it's going to max out at top speed. Otherwise, it will look at the rest of this. Now, I didn't want just this minimal amount trickling even when it's picking up the faintest amount of light. There at some point I wanted the motor to just stop. To create a minimum threshold, I made the volts at least be greater than 300. So if it's less than 300, it just gives it this 0 value, basically not telling the motors to move at all. I was having some problems that I was just picking up on the faintest amount of light, and the motors were just trickling, and it causes the most problems when you're trying to still drop the dominoes, because this is feeding information into the domino movement calculation to know when to drop the dominoes. To simplify it, anything less than that 300 volts evaluation would be zeroed out. Otherwise, it divides the volts by that 4 to give me that number. Example, if you have the 750 is your input here, you divide that by 4, since it is greater than the 300, to get what your total output would be for that, which should be your 187.5. So out of the 250, this is going to show 187.5 in your data. Because this is on a continuous loop, this is constantly sending information to this top, receiving the output, and that's what it's telling the motor speed. So you're going to get this continuous fluctuation of data input, giving the motor information on how fast it should be driving. So as soon as the light dims, it will slow the motors. And as soon as you add more light to it, it will speed up the motors, following exactly what is happening in real time. At this point, I have the domino dropping turned off. I was trying to drive it as fast as possible, and I didn't want to mess around with trying to drop dominoes as I'm moving fast. Like the line following does, it mitigates the domino dropping just for speed. Now you can uncomment this out just by simply removing the top and bottom comment sections. And this will now bring back the domino dropping aspect of the Domino Robot. The one caveat to this is at the top, you will want to play around with this value right here. The dispense distance, obviously if you're moving a lot faster and allowing the max output, you're going to need to adjust it so it optimizes it. Originally, this instead of being a 7 was a 5. This top speed also used to be 90. So keep in mind that that's where it started off with originally. I was wanting to optimize the speed movement with the light chasing robot. So one little trick, as you're doing some tests with serial monitor and everything, the problem is right now the motors are going to kick on and start running. So you're going to be chasing your robot. If you want to prevent that, you could turn the motors off right here just by adding the comment lines right in front of it. This will prevent the motors from running as you're looking at the serial monitor and testing it out. As you can see, I was taking a look at what the left motor speed was. Now you can also add what the voltage is at the beginning to understand where your voltage level is at. Yours may be different than mine based off of what the resistor is in your circuit for the LDR. I'd be curious to see if anybody else would be able to figure out how to optimize the motor output more than what is available here. Go ahead and do some research. While 255 is the maximum output from a code standpoint, you could probably optimize the motor output itself by just adding more power and current in other ways than how the Arduino is doing it.